this video, we're going to begin section 6.5 on improper integrals. Now, before we define what an improper integral is, I want to start with example 1 to give us some background on this topic that we're going to be thinking about. All right, so in example 1, it says a customer call center discovers that the fraction of their customers who wait between t equals A and B minutes to have their call answered is given by this integral. So in part A, we need to fill in the table or chart given. So here we're asked about wait times. So wait times between 5 and 10 minutes, and then what fraction of the customers wait between those 2 minutes. So we're going to use this integral to compute all of those values. And in each case, we'd have to compute this integral where we change A and B. Notice though that in all of these ranges that we're asked to compute, 5 is always our initial or lower bound. So rather than computing all of these 4 integrals, I could just let my second time be b and my first time be 5. So I can instead look at the integral from 5 to b of 0.2 e to the negative 0.2t dt. So by leaving this upper bound as b, that just allows us to make less computation. Okay, so let's go ahead and see what this looks like. So the main form of our integrand here has e to a power, but it's not a nice power. We have a negative 0.2 t in there. So we need to make a u substitution. So let's go ahead and do that. So let's let u equal negative 0.2 t. So then du is going to be equal to negative 0.2 dt. So dividing both sides by negative 0.2, I can substitute dt for dt here. And then I can substitute that exponent. I can substitute t. So what does this become? So now using u's, this becomes the integral where t equals 5 to t equals b of 0.2 e to the u du over negative 0.2. We can notice that that 0.2 cancels. So this just becomes the integral from t equals 5 to t equals b of negative e to the u du. So at this point, I could change these t's to b and u's, or I could just leave them as t's and then plug it in once we substitute back in for t at the end. All right, so let's go ahead and do that. So we can compute the antiderivative of negative e to the u, which is going to be negative e to the u. Now we're evaluating at t equals 5 to t equals b. So now let's substitute back in what we substituted for u. So that's going to be negative e to the negative 0.2t. And again, we're evaluating at t equals, and I can drop the t equals because I know that I'm just using the variable that I have in my expression here. So 5 to b, which is going to be negative e to the negative 0.2b minus negative, so that becomes a plus, e to the negative 0.2 times 5. So now maybe just carrying out one last step to simplify this final term because it has a weird exponent. We can simplify it quite a bit because we have negative 0.2 times 5 just gives us negative 1. So that looks like e to the negative 0.2b plus e to the negative 1. Okay, so this is going to tell us then the fraction of people who wait between 5 and b minutes for their call. So then in filling in this table, we can just use this expression that we just found. So let's go ahead and do that. So here for this first value, well, we're going to plug in b equals 10. So that's going to look like e to the negative 0.2 times 10 plus e to the negative 1. So we can compute that and we get 0.233. So we can think of this as a fraction or a percentage. and it's actually in decimal form. So it's the part of the whole that is weighting between those two times. So that would be maybe rather than percent, we could say decimal. A decimal is a fraction if we write it in the correct form, but we can also write fractions as decimals like this. All right, so then we can just continue to fill in here. So go ahead and pause the video and see if you can fill in the rest of the table on your own, and then continue the video to check your work. All right, so continuing here. Now we let B equal 20. We just plug in B there. And then finally, our final interval, we're going to have B be 25. So e to the negative 0.2 times 25. And when we put all those in our calculator, we're going to get then 0.350. And finally, 0.361. Okay, cool. Look at us computing all of those parts of customers or fractions of customers with those given wait times. Okay, so in part B, we're going to kind of look at things a little bit more generally. So part B says, what fraction of customers wait at least 5 minutes to have their call answered? So at least means that they waited 5 or more minutes. So this means 5 or more minutes. So again, we're wanting to compute an integral here where 5 is our lower bound. And what would our upper bound be here? Well, we need 5 or more minutes. So they could take 10 minutes. They could take 1,000 minutes. They could take 1,000,000 minutes to get their call answered. So in that upper bound, we're actually going to use infinity. So the integral then, using the same integral here, would look like the integral of 0.2 e to the negative 0.2 t dt. So now infinity is not a number in the sense when we've been able to compute integrals using an upper and lower bound. So what we have to actually do is rewrite b, or rather that upper bound, as a limit. So this becomes the limit as b goes to infinity of the integral from a to b, 0.2 e to the negative 0.2 t dt. So we can't compute an integral straight up with a bound that's not a number like infinity. So instead we interpret it as a limit. So now we need to compute the integral here from a to b of 0.2 e to the negative 0.2 t. So we've already kind of computed that integral up here, but now rather than, or maybe here, but rather than put in 5 in that lower limit, we're going to use a. So what does this become? All right, so let's go ahead and expand this term out a little bit so that we get a sense of what this limit is. Okay, so just copying down the limit as b goes to infinity of, so negative exponent means that we have 1 over the positive exponent, so positive 0.2b plus e to the negative 1. So e to the negative 1 is just a constant number. So what happens in this limit? So as b goes to infinity, the denominator here goes to infinity. It blows up. The exponent of e gets larger and larger, which means e to that power gets larger and larger. Looks like we dropped a negative somewhere here too. Up here, actually. So go ahead and make sure that could have been an issue in your calculations. I just dropped it in my writing, but all of these fractions should be correct still. Okay, so we actually get a negative there. No big deal. And just add that again. Okay. So we can think through what happens to this fraction as b goes to infinity. So the denominator goes to infinity, but the numerator stays at a fixed 1. So we can think of this as we have one, say, pizza, and we're dividing it into more and more and more people. Eventually, we're going to divide it into so many people that each person gets like no pizza. So this entire term here goes to 0 when b goes to infinity. So then this limit becomes, we no longer need the limit when we put evaluated. What happens to this term? So this becomes 0 plus e to the negative 1. And if we compute that in our calculator, we get about 0.368. So the fraction of people that wait at least 5 minutes is 36.8% of customers, or 0.368 of the customers wait at least 5 minutes. So what we've met in part B is an improper integral. So we're going to see that in this definition where we connect the example that we just used with the definition that we're going to meet in this section. So we define the improper integral, which is an integral from some fixed number a to infinity of f of x dx as follows. So we define it to be the limit as b goes to infinity of the integral from a to b f of x dx. So an improper integral has as its bound infinity. Okay, so now there's two types of behavior that we see in such integrals. So if the above limit exists and is finite, like we saw in part B of example 1, we say that the improper integral converges to a number. Otherwise, we say that the improper integral diverges. So that would mean it goes to infinity. All right, thank you for watching through this video. We are going to see some examples of both types of convergent and divergent improper integrals in the next examples. Thanks so much for watching.